Okay, so the question remains, why do we even want to transform functions? And we've had some hints when we referred back to the ways that we've stealthily used this in the past. But why do we need the whole technique if we can just do it by stealth? The answer is, we spent a lot of time and effort on graphing each new kind of function. And we haven't even graphed all of the kinds of functions that we met in this class. As we meet new and more complex functions, we want to be able to understand them easily as soon as we meet them. We also want to be able to say, this graph is very complicated. I would like to translate it somewhere and scale it somehow so that it becomes easier to deal with. We'll do this especially often in physics, where we'll set up our coordinate system to make the actual math easier. So here is a kind of function that we've met in this course, but we have not yet graphed. We're going to talk about how to graph this now. And we're going to use what we know about transforming functions to make this graphing much, much easier. So we have the graph here of y equals the square root of x. And I'm just going to pick out a couple of nice looking points on this graph. And I'm going to use those for my key points. So I think I'm going to use the input-output table method for this problem, just because I have a bunch of nice looking points. So my input and output, I'll have input 0 gives me output 0. And that's important because that's the special endpoint dot. Input 1 gives me output 1. Input 4 gives me output 2. And then we have this point where we have input 9 and output 3. So input 9 gives us output 3. Okay, so there we have some key points on our graph. I'm going to just go ahead and ignore that last one. I think we'll have enough. And next, from our input, we want to go back and find our x values. So the input of our transformed function is 2x minus 6. Our input is 2x minus 6. So our input plus 6 is 2x. Divide that through. Half the input plus 3 gives us our x value. So let's see. When the input is 0, our x value is 0 divided by 2 is 0, plus 3 is 3. When the input is 1, 1 divided by 2 is a half, plus 3 is, well, 3 and a half. When the input is 2, 4 divided by 2 is 2, plus 3 is 5. When the input is 9, 9 divided by 2 is, well, 9 halves. That's 4 and a half, plus 3 is 7 and a half. Okay, so that's my x values. Now, when I went from the input to the output, I actually did the square root. To find my y values then, I'm going to take 3 halves times that square root, and now I don't care about what's inside it, minus 2. So when my output is 0, 3 halves times 0 is 0, minus 2 is negative 2. When my output is 1, 3 halves times 1 is 3 halves, minus 2 is negative a half. Output is 2, 3 halves times 2 is 3, minus 2 is 1. Output is 3. 3/2 times 3 is 9/2. That's 4.5. Minus 2 is 2.5. So let's see. I have this special endpoint at 3, -2. And then I have a point at 3.5. That's here. -1/2. That's about here. These fractions I'm just eyeballing. Then I have a point at 5, 1. That's a nice point. And then I have a point at 7.5, 2.5. And more generally, I had a horizontal scale that's making things smaller and a vertical scale that's making things bigger. So I'm going to copy this general shape, but narrower and taller, using those points that I found for my location. And I'm going to have a graph that looks something like that. So that copy the general shape, but narrower and taller, I had to think about what the transformations actually were. Other than that, I just followed my points.